All right. So after giving some of you a double check on your heart rates, just kidding, group quiz today. Group quiz. You will need a calculator for that, so hopefully at least one person in your group has a calculator. There is mastering due tonight. We're going to finish chapter 7 today. And the next science seminar happens to be a chemistry seminar a week from today in here at 11 a.m. As a reminder, if you can't make science seminars, that's fine. Just email me. I'll send you back a video to watch that you can then summarize and get the same amount of credit that you would if you came to a talk. So I understand everyone's schedules are complicated. All right, so last time we met, this is where we finished off. We talked about atomic spectroscopy and that each element has a unique emission pattern that helps us make predictions about what elements are out there in space. So we can use those unique spectrums to figure out which elements are around. And again, this is a much better picture in color. So when you go to your textbook, look this picture up much better than it is in my sad black and white printer. So imagine that you have your hydrogen lamp going through a single slit. It'll then diffract, and we use a prism to move those diffractions apart in space. And so, right, white light is all, imagine this is color. All right, so we have, we'll start down here. Red, and over here we got some green, over here we got some blue. So white light is a continuous spectrum. Right, that it all kind of blends together. But an individual element will have a discrete line. So we can see helium has 1, 2, 3, 4, 5, 6. 6 lines. That's it. Barium has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Like 17 or 18 lines. And so we can tell, one, that helium is different than barium because they have different number of lines. And the lines are in different locations. So I can tell helium apart from barium using this method. All right, so that was a good experiment, but then we had to put that together with what we knew about the atom at the time. So the idea that each element has discrete lines required the scientists at the time to develop a new model for the atom. Right, so at the time we had that kind of like mushy model where there was electrons kind of out there, and definitely the protons and neutrons were in the center, but the electrons could be anywhere in the vicinity of the nucleus. But because there's discrete lines, it must mean that there are certain places the electrons always are. Right? They can't just be willy-nilly everywhere. We have to come up with a model that tells us that electrons can only be in certain spots. So the discrete lines meant that electrons could only be in certain locations. So Niels Bohr developed this new model to help explain this. So in this model, we're going to have electrons traveling around the nucleus in circular orbits. And then these orbits can only exist at specific fixed distances from the nucleus. Specific fixed locations. Which means we can think about it like as tracks, right? You're either on the track or you're on the next track. You can't be in the space in between. You're either on this one or you're on that one. All right, so then last time we talked about the photoelectric effect and that light came in discrete packets. That light came as a clump of energy. Well, that means must also be true for these electrons. So the energy of each orbit is quantized. Right, so if I say you have a quantity of something, it means you have a known amount, right? If you have a quantity of puppies, you have some number of puppies. Hopefully not more than like 5 or 6, because that's a lot of puppies, right? So that's your quantity of puppies. Same thing here. The energy has certain known amounts that we can measure. So quantized is just a fancy way of saying a known amount that's measurable. You can start using that in your everyday language. Got quantized how many puppies were in this basket. Good job. You counted them. You can think about that when you go home. I don't know, does anyone put puppies in baskets? All right, so now we have our energy of the orbit that's quantized. Only when an electron moves from one orbit to another is energy emitted or absorbed. All right, so electrons can be on a track, they can move to another track, but they can't exist in between two tracks. So you can think about like our solar system, right? You put the sun in the center, Mars has its circular pattern, Earth has its pattern, Jupiter has its pattern. You can't put Earth on Jupiter's track. That'd mess everything up, right? So everybody has their own lane that they're traveling in. So we can talk about how these tracks work. So the one that's closest to the center, so right here, this hard little, that is our nucleus. That's where all the protons and neutrons are living. The track closest to that is going to be called track number 1. Good, n equals 1. We're going to talk about what these letters mean here in a second. The next one out is 2, then 3, then 4, then 5, right? So the closest one is 1, farther away you get, bigger number. So So since I can only be on a track or on a different track, I can't be in between tracks, this means, I ran out of space, I wrote real big. And we call those tracks, in science we call them states. Whoever picked the nomenclature decided to call them states. So I can't be between states. I can only be in one or another. This means only specific known energies are allowed. So if I can only be here or here, and I know the distance between those two, I'll always know how much energy is needed to switch tracks. Right, since I can't land in the middle, I can only go from 1 to 2, or 2 to 1, and I know that energy gap, means I always know how much energy it takes to go from 1 to 2, 2 to 1. So there's two different ways we could travel, right, from track to track. We could travel increasing in number. I guess we, the electrons. Right, we could travel 1 to 2. We could start on the inside and move out. Or we can do the reverse. We can start on the out and move in. For me to be close to the nucleus and then move farther away requires an input of energy. All right, so if you think about where the electrons like to be close to the nucleus. That way the charge is all balanced. For you to push the electrons from 1 out to 2 requires that you've put some energy in to push them farther away. Right? Mm-hmm. All right, we could do the reverse. I can be at 2 and move in. When that happens, I'm going to release some energy. So these inputs of energy are usually in the form of heat. It's the easiest one to think about, right? If you heat something up, you're adding energy to it, which can help push the electrons out. When I release energy, we're going to give off light. So, looking at my picture that we have here, I have 3 different electrons. They're going from a high number to a low number. So if you can't see this real well, this is 5, 4, 3, 2, 1. Okay? So I have this first electron that's traveling 5 to 1. I have this one that's traveling 4 to 1, and this one traveling 2 to 1. Which is the biggest energy gap? The first one, the second one, or the third one? Right? The first one, I'm going from energy level 5 to energy level 1. Right? So I'm jumping 4 energy levels. Right, this is the farthest distance. Oh, sorry, it's only going to 2. You're right. Change those all. 5 to 2, 3 to 2, 4 to 2. In my picture, it looks different. Okay, so this is still this one right here. largest energy jump. So if it's the highest energy or largest energy jump, right, using your math that we learned on Tuesday, right, energy is related to wavelength. If you have high energy, you have low wavelengths. That's what this picture is also showing. Largest energy jump, shortest wavelength. Using our, right, the energy and wavelength are inversely related. If I have high energy, I have small wavelengths. Good blank stares. I'm assuming that means like super obvious. Let's move on. Okay. So then over here, I have my shortest energy gap. Shortest energy means longest wavelength. This chapter is tricky in that we don't calculate a whole bunch of stuff. It's mostly thinking through what it means. So it may change your study patterns for this chapter and the next 3 chapters. There's very little math in the next 3 chapters. It's mostly thinking about pictures and what they tell you. So if you are not a strong mathematician, quantum mechanics are for you until you take PChem, in which case they're not for you at all. So, how do we feel about this? Good conceptually so far? Okay. Let's see, what do I have next? Somehow I have missed a slide. There should be something in between 13 and 15. Oh, there we go, 14. All right, so let's talk about this wave particle duality. So it's been shown using a variety of experiments that I would love to talk to you about sometime if you're fascinated. But for now, you just take my word on it. That's been shown that the wave nature of an electron is a property of an individual electron. So it's not a collective property. Each electron has its own wave that it performs. So from this, we can we'll talk about this de Broglie wavelength here in a second. So from this fact that electrons have their own wave function that they have, we're going to be able to make predictions on de Broglie wavelengths, uncertainty principle, and indeterminacy. Throw these around this week and you're going to sound super smart if you want to talk about the uncertainty principle. When you get there, you'll be like, oh, that totally doesn't make any sense at all. That's all right. All right, so let's talk about this de Broglie wavelength first. Right, so an electron, being a particle of light, has both its particle nature and its wave nature. And so an electron traveling through space is going to be making a wave but acting like a particle, which is mind-blowing unto itself. But we'll talk about the wave function of it first. So an electron's wavelength right, like we talked about earlier, energy and wavelengths are related. And they're moving through space. So it's related to its energy, comma, its mass, and its velocity. So we can relate these mathematically. Where I say wavelength is equal to Planck's constant divided by mv. Now, don't get confused. These are not the m's and v's we've used before. These are different m's and v's. In this case, m is mass in kilograms. And this is a regular v, not a tipped over nu. This is a regular v. So this is our velocity. And since the velocity, we're going to use meters per second. So this means I can now predict a wavelength knowing the velocity of an electron. Pretty cool. So let's go ahead and do that. Go ahead and fish out your calculator if you haven't already. This is going to be a good chapter that I know you all bought a book, at least an online book. This will be a good chapter for you to actually sit down and read. I know people don't like reading books, but this will be a good one to kind of look through and like read what they have to say too, because this is the least intuitive chapter we're going to look at. So if it's baffling, I recommend reading. I always recommend reading, but for real, I mean at this time, actually read. All right, so let's calculate the wavelength in nanometers of an electron that I put my radar gun on and measured it to be 4.57 times 10 to the 6 meters per second, which you can't actually do, right? Because by putting my radar gun on the electron, I force it to do something crazy. Look at there. Okay. So imaginary, I know the electron's speed. So things we need to know for this, right? We also need to know the mass of an electron. That wouldn't hold up in court. If you had the radar gun and he caught you speeding and say that the radar gun actually forced your car to go faster, it doesn't work on the big scale. If you're an electron, then you can get away with that in the court of law and say, by looking at me with your radar gun, you've actually caused me to speed up. Not true for a big car. All right, so the mass of an electron is 9.11 times 10 to the negative 4th kilograms. So we're going to go ahead and plug that into our equation. All right, what's one issue we see right off the bat if I want to be in wavelength at the end? I got nanometers and meters, and I got those funky joules in there, right? There's nothing right now that can cancel them out. Don't worry. Turns out, you would never know this off the top of your head, but if you went to the back of the book, you would find out that a joule is equal to a kilogram meter squared per second squared. Turns out, funny enough. So you can either just squish that right in there, erase the J, and put it in there, but I'm just going to rewrite it. All right, now we're ready for some unit canceling. All right, what is one thing that can cancel out unit-wise top to bottom? Okay, I can definitely get rid of some of these seconds. I can get rid of that one and that one. What else can I cancel out? Yep, the other seconds, that and that, and then the kilograms. And then what's left? Yep, I can get rid of one of those meters, one of those. Question? Oh, because it was joules times seconds, and I just changed the joules to this crazy thing. And I gotta leave the seconds. So what unit do I have left? Meters. Success. So now we just need to put it into our calculator and do a little converting. All right, so let's see. My math has been a little off today, so everyone double check me. 4 divided by... Yeah, okay. That makes sense to me because I got -34 and -31, so that'd be positive, no, -5. So yeah, so that's about the right ballpark. Are we done? No, I need to get into the nanometers. So I ran out of space, but you could just keep converting over here. So we take that. Which makes sense. -10 times +9 will be -1 as your exponent. So that would scoot over 1 decimal point. Yay! Hopefully one person in your group is feeling confident about math today. Because we're going to do some of these I'm going to say there's a good chance. Something like, not this problem exactly, but something where you plug it in and convert to nanometers. Good chance it's on your quiz. Strong chance. Strong. Feeling strong about that. Having written it, I feel like I have first-hand experience. All right. How is that? Good. I know the speed. I convert to wavelength in nanometers. All right, I'll wait for everybody to catch up. We'll take a minute. Because we're getting ready for the 2 concepts that are going to be more confused than anything else we've done. So, if you were confused, you'll be more confused. If you weren't confused, you will be confused. So, yay! So let's talk about this uncertainty. So that's the Broglie wavelength. The second thing, right, is this uncertainty principle. All right, so the uncertainty principle says that we can never see an interference pattern and simultaneously determine which hole the electron goes through to make it. So, right, if this is my beam of electrons, it's going to make the interference pattern like we saw on Tuesday where there's distinct light and dark lines. We know that's going to happen, but there's no way to know exactly which electron is hitting someplace. Because we see this, but if we thought about it as particles, like if you thought of, if you had a tray of marbles and they only had 2 slits to go through, in theory, right, if you did this in your head, they should come through in 2 straight lines. Right, there's only 2 spots for them to come through, which would be true if they're acting as a particle. But because electrons are acting like waves, they do like we saw in the video on Tuesday where they interfere with each other and we see a bunch of lines. So, I have this. No. I'm just write it in the back because I don't have enough space with all the pictures. So you may have heard of this, the Heisenberg uncertainty principle. Maybe not. You have now. Good conversation starter for your parties this weekend. Be like, hey, I learned about this thing called the Heisenberg uncertainty principle. Let's talk about it. It may not work as a pickup line. May not. You never know, though. You find the right person. And they'll be like, I do know about that. So this is what we just did, right? We related the velocity of the electron to its wavelength or its wave nature, right? We have math. We just did that. We can show that if I know how fast it's going, I know what wavelength it makes. There's some combination of that. When we talk about position, like where we expect an electron to be, well, that's only if we're thinking about it as a particle. So if I know the velocity, I know its wavelength, but I don't know where it's going to be. Or if I know where it's going to be, I don't know what wavelength or velocity it has. Because you can't think about an electron having both properties at once. You can either say, oh, I know its speed, so I know its wavelength, or I know where it landed, so I know some other things about it. So more often we state it like this. The more accurately you know the position of an electron, the less accurately you know its velocity. Because if I know the position, I'm thinking about it as a particle, so I don't know its velocity because that's its wave properties. Or if I'm thinking about it as a wave, I know its velocity, but then I have no idea where it is. So you can't make a prediction based on both. You gotta pick one or the other. So either velocity or position. And that's the uncertainty principle, that the more you know one, the less you know the other. You're uncertain about 50% of its properties. Good? Mm-hmm. I'll wait for everybody to catch up. Because then I have a video. Oh, we can take a little break and watch a video. And then we'll talk about principal quantum numbers. Yay, quantum numbers. Those are my favorite things to talk about this semester. Favorite things to talk about this semester. Next semester, if you take 109, we're going to do ice tables, which if anyone is any of your friends are in my class right now, they know how passionate I am about ice tables. Ridiculously passionate. All right, so let's talk about, so that's uncertainty. Indeterminacy. I don't know how you can take this class and not be like fired up about chemistry all the time. Be thinking, man, this is the best class I've ever taken. I wish I took more chemistry. You can take lots more chemistry. All right, indeterminacy. So, like we just said, if we have a macroscopic object, right, which is, you can see it, right, big, you definitely know their velocity and position. Right, you can see a car driving, figure out how fast it's going, and by you measuring how fast it's going, it doesn't disappear. Right, so it's determined. Electrons, based on our uncertainty principle, don't have their velocity and position known. It is indeterminate. So, while everyone's finishing writing down that one fantastic sentence, I'll have to turn on the lights a little bit.
We will take an example to understand uncertainty principle.
He's Germany sounding.
Let there be a blindfolded person in a room searching for a ball whose velocity he has been told but not the position. He will come to know the position of the ball when the ball collides with him. But at this point of time, the velocity of the ball would have changed due to the collision. This is precisely what Heisenberg stated, that exact velocity and exact position cannot be determined simultaneously.
And it's a real short video.
Welcome to this video, which is about Heisenberg's uncertainty principle.
We don't want to watch that. That's an actual full-on lecture about Heisenberg's uncertainty principle. So, since by searching for the electron, we don't know where it is, we think about it in a different way. So while we don't know exactly where to look for the electron, we'll know in general where to look for it. So that's what this picture down here is trying to show. Right, so if we threw an electron, if you threw an electron, right, based on your regular physics, we can predict where it's going to land, right? It has so much up, and then gravity pulls on it, and then it comes back down. You can kind of predict where it's going to land. Indeterminacy says we don't know exactly how fast it's going, but we can make a good guess it's going to follow about the same path. It may just be up here, it may be down here, it may start up and then come down shorter. So we can use probability to predict where an electron will be. That's what indeterminacy is, using probability to determine the location of an electron based on the fact that we don't know exactly where and how fast it's going. We can use probability to figure it out. All right. Ready for the big conclusion for this part. All right, so now we know lots of things about an electron. We know that you don't know how fast and the location of an electron. We know that if we know the wavelength, we can figure out the velocity, or vice versa, velocity, wavelength. We know that they have discrete packets of energy, which means they have only certain spots they can be at around the electron. So how does that help us with our everyday chemistry? In the area of quantum mechanics. So, like we've talked about a lot, right? Properties of an element are based on the electrons, mostly, right? Because if you change the number of protons, the number of neutrons, it can affect how the element's working. But the number of electrons we can change. We can make it an ion of some sort. We can make it bond with somebody else. We can do all those kinds of things. So properties of an element is dependent on the energy of the electrons. And if we know the energy of the electrons, we then know the velocity of the electrons. But the velocity and the position, right, are indeterminate. We can't know both. But, big but, and I can't lie. I just finished singing that song in my head. I was like, I'm just going to say it out loud. It's funny. for each electron state, we can specify, right, the states where the individual tracks that the electrons are on, each one of those states. We can specify the exact energy. All right, so if we know what state it's in, we can tell you, oh, if it's in that first state, it has this much energy. If it's in the second one, it's this much more energy. Right, so we can tell things about that. So while we don't know the exact location of an electron, we can describe the space the electron is likely to be found. And that space where the electron is likely to be found, we call that an orbital. So, if we know the energy of an electron, which we can measure the energy of an electron. We won't know exactly where it is, but if we know the energy, we have a really good way of predicting, using our probability calculations, where we can find it. So we don't know exactly where. We have a good guess as to a zone, an orbital, where it can be. So one way we can describe it is using this thing called the Schrödinger equation. So a wave function, which is given the abbreviation psi. If you're having a hard time thinking about what letter that is, it looks like a trident, right? If you ever watched Little Mermaid, like Poseidon, that's where they get psi from. Psi, trident, Poseidon. There's your fun fact for the day. There's another conversation starter. All right, so the wave function, which has the symbol psi, is a way to describe energy of electrons and the probability of finding an electron in a given volume of space. I would love to tell you more about this. There's a whole class called physical chemistry that's all they work with. They figure out how do we know how big a space, how we make those probability predictions. We're going to skip a bunch of that and just go to, we know this is true. And what can we gain from that? So in this class, we're going to describe a wave function using four quantum numbers. And these four quantum numbers will just tell us approximate energy, approximate location, and likelihood of its spin state. So those four numbers will tell us just about everything about this electron. So you can kind of think about quantum numbers like a ticket. So right, if you go to a concert venue, on your ticket, assuming it's not just general seating, that you have an actual assigned seat, your seat will tell you which section you're in, right? Maybe which zone, which section, which row, which seat. So that you have one specific seat in the entire auditorium. That's what these four quantum numbers describe an electron. It's going to tell us what zone, then which section, then we can zoom in, and then we can zoom in. And now each electron has a unique set of four quantum numbers that only go with that electron. So each electron has its own seating in an atom. So let's talk about what those four numbers are. The first number describes the principal quantum number, which is given the abbreviation n. We've actually already looked at this. This is when I had my Bohr model, and I had the little circles, and I said 1, 2, 3, 4, 5. That's what this was describing. It was describing the overall size and energy of the orbital, which the orbital was the zone, the volume of space I'm going to be looking in. So when I say an integer, does everybody know what I mean by an integer? It's a whole number, right? So right, 1 or 2 or 3 or 4. So here I have a little plot where this is energy, increasing going that way. And I have different locations that the electron can be in. I can have n equal 1, 2, 3, 4, right? And as I go up in number, the energy gets higher. So just like we had in that picture, where the farther away I am, more energy. More energy to either push it out or more energy released to drop it back in. I think that spelled right. E-N-E-O. So as n gets larger, the energy increases. And that means that more energy is required to force an electron from this low energy level to any other. Right, it's saying I need more energy to go from 1 to 2, and even more to go 1 to 3, even more than that, 1 to 4, because I'm pushing it farther away from the nucleus. Then the other thing you may be thinking is, these are negative numbers, which is a little funky, right? Energy is a negative number. So the energy is negative because as n gets larger, I'm farther away from the nucleus. Right, so as I get farther and farther and farther away, you imagine at some point it just breaks free. Right, it's kind of close, it's being held in by the nucleus, kind of farther, a little less interaction. Even farther than that, less interaction. At some point it's so far away you can't even tell where the nucleus is anymore. Right, we consider that a free electron, just broke loose. Not really, but you can imagine that it broke loose. When it breaks free, that energy has to be 0, because there's no way to bring it back in. So while the energy is increasing, it's increasing more negative until you get to pretty much 0, at which point it's just loose. All right, so n is a whole number that tells us the energy of the orbital. Right, so that's the zone. It tells us what zone we're in. All right, so our next number is the angular momentum quantum number, which has the abbreviation, that's a terrible looking, that should be an L, not an I, L. Big old scripty L. So N tells us the approximate size and energy of an orbital. L tells me what shape the orbital has. And L will be any integer between 0 and n minus 1. So we think about it like our 4 numbers, right? We have our zone, which is n, and you can have any value of L up to whatever 1 minus your zone was, n minus 1. So for example, if I had an n equal to 2, my options of L could be 0, could be 1, or 0 or 1, right? Because that's starting at 0, everything up to n minus 1. Let's say I had an n equal 5. What are some of my possible values of L? Yeah. Right? Those are all my options. Okay? All right, so then these values of L if it wasn't confusing enough, these values of L are assigned numbers, or they're assigned numbers and letters. So, those are going to be the values of L I care about, 0, 1, 2, and 3. Those are going to be the 4 I need you to know. If you have an L equal to 0, we call that S. So those are all equivalent. L equals 0, L equals S. If L equals 1, that's equal to P. L equals 2, that's equal to D. And L equals 3, that's equal to F. This will make sense once we kind of put it all together. So now I have a number / letter value. These L values are unique shapes. Yeah.
Is that supposed to go all the way to F, or is that only S, P, and D?
Those are all the letters, S, P, D, F. Yep. I don't know how they picked it. That's what they went with.
So we're not going to use G at all?
For all the elements we're going to be concerned about, we just need to know these. All right, so each L value has a unique shape. I'm terrible at drawing in 3D. So if you don't have this PowerPoint, definitely go to the book or get this PowerPoint because I don't do well drawing in 3D. All right, so again, we have our unique shapes. So this guy is L equals 0 equals F. So L equals 0 equals S tells us that is a sphere, right? Big old round sphere. It's also going to be our lowest energy, right? If we know that L can only be between 0 and n minus 1, 0 is going to be the lowest energy. So this is our lowest energy shape. these are my three ways I could draw L equals 1 equals P. And I'll tell you why I have three options here in a minute. So the P shape is kind of a dumbbell shape where it either's along the X or the Y or the Z axis. There's three ways to. All right, this is going to be slightly higher energy than this one. L equals D. What? Have a dumbbell along the in Y along X along Y, or this was dumbbell. They're volumes, so to draw this volume. All equal volume. Just a different. So big have are 3. How many shapes should L3 equal F have? Of it. Look. Equals 3 should have. Ask you 3 by these shapes. Circle them. All right. That's N. So the N one of the orientation of the IGN. Magnetic sub F. Tells me orientation to be looking times electron. And then L is L. Look at some examples of hacks out. Okay, three options. Over one. All right, so equal letter to this. Be N between plus L of M. So how many just have? I only had a question. Oh. Our sphere. It's in L equals that go P L equals M negative plus 1. How many is P? So let's 3 3 because us to draw. So then let's those two. Should there check? So if there's station, expect 5. Minus 2 minus 1, 2. So if I have to draw, that's what you got. might be. This is proving a had minus 4 plus is minus five. That's our year. Equal to. I can have one. I can minus 1 0. So you can see more space to put 11s because energy. Second energy, I can now have 4 in the and I can see a triple not more energy. All right, I'll this will kind of roll chapter 8. So if you bring your the little quantum magnetic spin. And some of our other having in the same the same amount. That's quantized. Full value. Choose 1/2. This 1/2 and space. I have two to get up down. Cancel each other. Okay. Now I have to do the homework tonight. Back up this camp. Start chapter 8. This why are the able out those guys ion or anion? It's good stuff.